Hello there, my name is Dylan and I'm going to talk about some EE concepts in this video. I wanted to get all the ideas that you really need to be familiar with to get through Bode plots kind of condensed into one video, more as a refresher for people trying to remember how to do all the steps up to Bode plots, and then maybe as an introductory thing if you haven't seen any of these topics yet. Maybe this will be helpful, maybe it'll be confusing. I don't know, we'll find out. So we're going to talk about sinusoids, phasors, impedance, and then frequency response at the end, walking through transfer functions as well as Bode plots. So starting out, we've got sinusoids and AC circuits. So when we're talking about doing AC analysis, we're really talking about using sinusoids. And a sinusoid is a sine wave or a cosine wave. It can be either of them. It's not just sine when we're talking about sinusoids. And when we're talking about alternating current, that's what AC is. AC circuits are alternating current circuits, which means that it's a current that's going to take the form of a sinusoid. So it's going to have a positive half cycle and a negative half cycle. That's why it's alternating. So any source that's governed by a cosine wave or a sine wave, either a voltage source or a current source, will be producing alternating current. So this is why it's called AC analysis. And so our AC waveforms take this standard form where A cosine omega t plus phi. A is the amplitude. A is representative of this maximum value, this peak value, or this negative peak value, but we're just going to use the positive value for our amplitude in our expression. This parentheses is the argument of the expression, and inside that argument, we'll find the angular frequency omega, that's in radians per second typically, and then we have time and phi. This is the phase angle, represented by the Greek letter phi. Phase angle means how far along this axis, typically our horizontal axis, that we have shifted our sinusoid, kind of a way of representing how far along it has already progressed relative to another point. So when we are talking about AC circuits, almost the very first thing that we talk about is that we would actually prefer to have them not in the time domain at all. We'd rather have them in the frequency domain when we're solving problems. And the reason for this is because if we have a circuit containing inductors and capacitors, that we're going to have to do differential equations. And differential equations are long and they are complicated, and we don't want to do them. So rather than going through this whole process with a second order differential equation, if we get into the frequency domain, we can skip this dilemma entirely. So to pull everything into the frequency domain, we're going to have to convert our source, our voltages and our currents, into the frequency domain. And we're going to have to convert our components, that is our inductors, resistors, and capacitors, also into the frequency domain. So if we're talking about taking our sinusoids into the frequency domain, that's going to consist of putting it into a phasor form, where a phasor is defined as a magnitude at some angle. There's actually more than one definition of a phasor, but this is the most used definition when we're talking about converting back and forth between a sinusoid. And so this magnitude R is the same thing as the amplitude of the sinusoid. That's the peak value. So we could just say that that peak value at the top there, the highest value that the sinusoid will reach, that is also R. And then the phase shift is just how far along the axis it has shifted relative to some other point. So either relative to a standard cosine or sine wave, that's usually what we're talking about. It's like relative to how they normally look. And so that's how we can pull it into a phasor, but we actually want to know a little bit more about phasors rather than just that. We should talk about the complex plane if we're going to talk about phasors. So the complex plane is a plane that plots the real and imaginary axes against each other. So the real is the horizontal and the imaginary is the vertical. And when we say imaginary, we mean the same imaginary number I that you learn in pre-calculus, where we define it as radical -1, but instead of being I, it's going to be J here. The reason for this is because I is current, so we can't use I to represent the imaginary number negative radical 1 anymore, because that's been taken. So instead, we do this. We say it's j. And to represent a point on this complex plane is really describing a phasor. So we have two ways of doing this. So it's like if we want to describe this point right here, we can either describe it in polar form, which is to say similar to a vector form, where it's some distance from the origin, r, that's the magnitude r, and then it's some angle off of the real axis, that vector. So that's what phi represents. So r at an angle of phi, that's the polar representation of a phasor. That gets us to this point. That's what the phasor is representing. There's a second way to represent this point, though, using the x and y coordinates here, or rather the real and the imaginary coordinates. So we could say that that's x plus jy will also get us to this point. That's called rectangular form, x plus jy. And you see there's all these equations I've written down where r can be described in terms of x and y, and phi can be described in terms of x and y, and x and y can be described in terms of r and phi. So we're able to freely convert back and forth between these two using these two sets of formulas. The only time we have to do this is when we're manually doing phasor math ourselves. If we're trying to add polar numbers, we actually can't. We got to put those in rectangular using these equations first. And so that's how we represent our sinusoids. We put them into phasors to get them into the frequency domain. But we also have to convert our components. So R, L, and C in the time domain are going to have to come over to the frequency domain. This is converting them into an impedance. So instead of having different values and different analysis methods for each component, if we convert them all into this impedance unit, we're able to have them all be treated equivalently, almost like every component, R, L, and C, are resistors. This is hugely beneficial. So the impedance itself is represented by the letter Z, and you can think about it as opposition to alternating current. So it's how well it opposes AC. So it's like AC resistance is a good way of thinking about it. And so similar to resistance in DC circuits being equal to V over I, resistance, or impedance, I should say, impedance, Z, is equal to the phasor V, that's what this little hat means, this arrow, that's phasor V over phasor I. And so to create those impedances is just a simple equation. It's just a normal formula. So in the time domain and the frequency domain, a resistor is actually the same. So it's just R no matter what. However, the inductor, instead of being L in the time domain, is now described as J omega L in the frequency domain, where J is that imaginary number, omega is the angular frequency in the argument of the sinusoid that we pointed out earlier, and then L is the inductance of the inductor. Similarly, the impedance of the capacitor is represented by 1 over J omega C. You can figure out the values similarly to the inductor. And so that's how we can pull all of our components into the frequency domain. If we bring both of those ideas together by pulling the voltage source or whatever other source you have into the frequency domain, and we pull all of our components into the frequency domain by converting to impedance, we suddenly have a much simpler situation. This is because that impedance relationship, that Z is equal to V over I, that enables the use of Ohm's law, because we can manipulate that to say that the voltage in an AC circuit is equal to the phasor current times the impedance. And because we have access to Ohm's law, we also have access to all of our other DC analysis techniques. We have access to Kirchhoff's voltage law and mesh analysis that stems from there. We have access to Kirchhoff's current law and nodal analysis, which stems from there. We also have voltage division, current division. We can make Thevenin equivalencies much easier, superposition, all sorts of tools that we learned in Circuits 1 are now eligible for use in AC circuits. And perhaps the most beneficial part of this whole thing is that the expressions you get from performing these techniques will be algebraic in nature. You'll have algebraic expressions or equations that are not going to require differential equations. So the time to complete a problem will be dramatically lower, and also it'll be substantially easier to complete. Not always easy per se, but easier than they would be if we were doing differential equations. So that's a lot about kind of AC circuits as an intro. And then frequency response is a different kind of AC circuit problem. It's similar to AC circuits in that we're using sinusoids, we're using AC analysis still, but for a different purpose. Now, instead of having one value for omega, for example, if we have 6 cosine of 5t plus 30, that's a situation where omega is 5 radians per second. Or here, we have an example where omega is 8 radians per second. If we instead change from these types of problems into situations where omega does not have a numerical value, like what if omega was varying over a range of frequencies? That's when we start to look at frequency response. Because now we're interested, how is the circuit going to respond as we change omega? So if we have this circuit or any other circuit, any changing value of omega, what's going to happen? That's what we're trying to answer when we're talking about frequency response. How is the system going to respond? And to kind of illustrate what this is describing, let's look at the following pictures. So say, for example, we have an input sinusoid, we have an output sinusoid, and the way we got this output sinusoid is by passing this input through this system. And the resulting output is this one. We can see that the input has some peak value, which I've written as R here. So we have R and some phase shift, phi. So we could describe that in polar as R at an angle of phi using the polar setup we described earlier. And then the output also has R and phi, the peak value here, the peak of the sinusoid, and the phase shift of the sinusoid could be described as the output magnitude and output angle, R out at an angle of phi out. And then the system itself can be described to have some unknown magnitude and angle, R at an angle of phi, both of the system. And so we're after the system's response. And in order to do that, we can make this 3-picture diagram into an algebraic equation and then kind of manipulate it a little bit. We can say that this output is really the result of multiplying these two things together. This input with the system gets us to this output here. And so we can say that our input magnitude and angle times the system magnitude and angle will be equivalent to the output. From here, it's simple algebra to just move the fraction over and get that the system is equal to the output over the input. And this is a very important situation. This is called the transfer function of the system, which describes the output of the system relative to the input of the system. So it's the output relative to the input. That is described by this transfer function, which is just this ratio. We're typically after this transfer function when we're describing frequency response, because this is what allows us to really look at the answer to the question is what's going to happen as omega is changing. If we have a transfer function, we'll be able to determine that. And I'll describe that by example. So if we have a little circuit here, we have R and C, and we're interested in the transfer function. We'll say the output is across this capacitor. We can define the output however we want when we're doing circuit analysis. It'll change the transfer function and the system response, but here it's described as across the capacitor, and the input is the actual voltage getting fed into the circuit. So the transfer function we're after is the output across this capacitor relative to the input from the source. We've already put this into the frequency domain, so this is an impedance instead of a capacitance, so it's 1 over j omega c. The resistor stays the same in time and frequency domain, but the input voltage and the output voltage are both also here represented as phasors, just denoted by the hat. So we are trying to create this transfer function, and we can do that using voltage division, because this is a textbook case of voltage division when we have one series path to ground. Doing that, we'll get the expression V out is equal to V in times this ratio, where the numerator is the impedance we're after, the denominator is the sum of all the impedances. And then we can manipulate this equation and kind of clean it up a little bit into this one. where we get V out over V in is equal to this expression here. And now this is the transfer function, V out over V in. As soon as we've made that ratio, we have made the transfer function. That's what we have just defined. And so with the transfer function in hand, we can then begin to answer the question of what is the magnitude and the phase of the transfer function. And we can do that by looking at our polar definitions that we laid out earlier. We said that the magnitude R was just x squared plus y squared on the earlier page. I had written out these equations, and those are still going to hold true when trying to find the magnitude and the phase of the transfer function. It's the same approach. So it's just a combination of the real and the imaginary values, where y represents the imaginary and x represents the real. So applying these formulas to this transfer function, we can get that the magnitude is just the magnitude of the numerator over the magnitude of the denominator. And that is to say that we'll get just 1 in the numerator, because the square root of 1 squared is still just 1. And then the denominator will be the real term 1 squared, which is just 1, plus the imaginary term squared, which is omega RC squared, all under a radical. We can do the same thing with the inverse tangent over here. That is the phi equation. That's how we get our phase of our numerator and denominator. The numerator has no imaginary, so it'll have no angle. It'll just be 0. The denominator will be negative tan inverse of omega RC over 1. This turned into subtraction because we're handling two different polar numbers, and when we're dividing polar numbers, we can treat it like subtraction. And so we get these two different expressions for the magnitude and the angle, and we can plot those at different omega values. If we could just do kind of a basic example and looking at omega is 0 and omega is approaching infinity, and see that the magnitude when omega is 0 will boil down to 1 over 1 plus 0, which is just 1, and that the infinity case, as omega approaches infinity, the magnitude will boil down to 1 over radical 1 plus infinity, which anything over infinity is going to be equal to 0 as that denominator increases dramatically. And so at low frequencies, at 0, it's a value of 1, and then as our as our frequency is increasing, we're going to get a magnitude of 0. So we're going to go from 1 to 0. Similarly, with the phase, if we look at the equation and plug in 0, is going to provide negative tan inverse of 0 degrees, which will result in 0 degrees. And if we plug in omega approaching infinity, we're going to get negative tan inverse of infinity, which is the same thing as negative 90 degrees, because tangent inverse of infinity is 90, so it's negative 90. So this is varying from 0 to negative 90 as omega is increasing. So from 0 to negative 90. So this is a generalized case for doing this. We can always perform this process, but sometimes it's more complicated and sometimes there's more terms involved. And it's actually a little bit more complex in that we need a different approach to making these graphs, especially when we have a bunch of different numbers involved. And that approach that we usually take, that process, is the process of making Bode plots, which is our next topic. So if you're making Bode plots, the first thing that we're really doing is that we're converting all of our magnitude into decibels, where decibels is defined as 20 log 10 of some value. Here it's going to be 20 log 10 of the transfer function. V out over V in, or I out over I in, whatever our transfer function may be, some output over some input. And the reason we need to do this is that we are after a logarithmic scale. The reason is that if we look at a range of frequencies, say some very small frequency, 0 or 0.1, all the way up to 10 mega or beyond, that's 10 million, if you look at that number in scientific notation. And then if we wanted to actually plot that, omega as the x-axis is going to have to go linearly from 1, 2, 3, 4, 5, 6, 7, 8. You're never going to reach 10 million. This would take pages and pages of expanding this axis, and you would not want to do that. Even if you could, it would take forever. And so we need a logarithmic scale, because a logarithmic scale is based on decades, which a decade is 10 times the previous value. So 0.1 times 10 is 1, times 10 is 10, times 10 is 100. The next tick would be 1,000, and so on. This will take many ticks to reach 10 mega still, but substantially less ticks than the linear scale. It's for this reason that we choose to use the logarithmic scale, which is what requires decibels, because this is a logarithmic unit. So that's why we have to convert our magnitude into decibels first. Because we're using a logarithmic unit, our log rules are going to come back from pre-calc, which you may or may not remember. So the log rules tell us that if you have two terms being multiplied inside an expression, that we can break that apart into two logs where they're being added together. So it'll be log of P1 plus log of P2. If we're dividing, it'll be log of P1 over log of P2. That turns into subtraction. So it'll become log of P1 minus log of P2. If we have a term raised to a power, we can turn that power into a coefficient. We can pull that n out front, as we have done here. So these are the three rules that we have to remember primarily when we're working with decibels, just because it's a logarithmic, and this is really fundamental to how we use the unit. When we're making the Bode plot itself, it's going to be a transfer function broken apart with these rules, and it'll be broken apart into these factors that are on this table. So this is a table that I pulled out of a textbook, roughly, and these are available online in any kind of standard circuits book. You can find these kind of all over the internet if you're wanting one of your own. And these are really what you need to make a Bode plot, make it easily, I should say. You can make it in other ways, but this is probably the best way to do it. So we want these factors to be how our transfer function breaks down into these recognizable forms. And if we do that, if we create these factors, we're going to have a reference of like, well, this factor will then correspond to this magnitude in this phase. And that applies to all of these factors. So you have a map of what your plot will look like term by term. So for example, if we have a transfer function, g of j omega, that is equal to this expression, j omega plus 2 over j omega plus 10 times j omega. This is an example problem that we can apply this table and these log rules to illustrate what is really meant by a Bode plot, how to make it and what we get out of it. We can see that these original terms, j omega plus 2, j omega plus 10, these are not on the table, the Bode plot table. These almost look like this form, but they're not, because we're not adding plus 1, right? We're adding plus 2 and we're adding plus 10. So we need to force that to be a 1 so that these two magnitude and phase plots will apply to this case. So we do that here by factoring out a 2 from the numerator and a 10 from that parentheses, that j omega plus 10. If we pull 10 out of there, that's a 1. If we pull 2 out of the top, that's a 1. So the factored out 2 and 10 are out here, and the inside becomes j omega over 2 plus 1 and j omega over 10 plus 1. We can then simplify the numbers. We can pull those up top to be 2 over 10 is 0.2. And this is the standardized, which is to say it'll fit into this table well, the standardized form of the transfer function. So now I've labeled these 4 different terms, each of the different pieces on here, and I've labeled them again down here because we need to break this into its magnitude and its phase. This is the magnitude of this expression written out according to these forms on the table. So a factor k, which is just a constant, will have a 20 log k magnitude. And we can see that 20 log of 0.2, 20 log of 0.2 is negative 14. You can type that into a calculator yourself. 20 log base 10 of 0.2, that's negative 14. You can verify that yourself. I encourage you to do that. And then that's this first term. I broke this down into 4 different terms over here, 2 being added and 2 being subtracted, by applying our log rules from 2 pages ago, which says that if we're multiplying 2 terms, I can break that into 2 different terms added. And if we're dividing terms, that's the same thing as having subtraction between those separate logs. So in that sense, we're able to subtract anything that's in the denominator. So the numerator terms, the 0.2 and the j omega over 2 plus 1, those are being added. That's 1 and 2 over here. And then 3 and 4 are in the denominator, so those are being subtracted. And all I've done is apply the 20 log 10 definition. This is what we defined logarithms to be, or not, this is how we define decibels to be. So these are all now in the decibel format, okay? So now we take these 4 terms and we look at the magnitude plot that we're trying to create, and we say, well, this first one is just -14. So I'm going to plot that on my Bode plot. I'm going to plot that here on my, excuse me, I'm going to plot that on my vertical axis. -14 is what that corresponded to. My vertical axis corresponds to decibels, my magnitude in decibels. And so that's going to come in the form of this. I'm going to plot each of my 4 terms as a dotted line to represent how that individual component contributes to the overall Bode plot. So my first one is just at -14. It's a constant value, and that's what we found it to be, and that's what the table says it should be. It should just be a straight line. The second term is 20 log 10 j omega over 2 plus 1, this guy. That is going to be of this form, right? 1 over j omega over z, where z is 2 in this case. And that tells us that when it hits 2, it's just going to start rising at 20 decibels per decade. So just applying that, when it hits 2 on the omega axis, it's going to start rising at 20 decibels per decade. That's term number 2. We do that for each of these 1, 2, 3, 4 terms. Each of them are going to follow a format based on this table that we check, and then we plot them with dotted lines here. And then in the end, once we have all 4 of them out, then we're just going to add them all together. We need to figure out where it's going to start based on what terms are hitting the y-axis. So that's 20 is on the y-axis from this term, and -14 is hitting the y-axis here. Just adding those 20 and -14 gives us a starting value of 6 decibels. And then we'll just start combining the slopes. So the standard slope is 20 decibels per decade. So the only active slope here is at the y-axis is this 4th term. The first term is flat. It has no actual slope. The second term and the third term don't start until 2 and 10 respectively, just based on how their plots came out. So 4 is the only active component here, and it has a -20 slope. So -20 until we reach the next active component, which started at 2. And so this is now +20. This was -20. The 2 of them cancel out. So we're going straight until the next component comes into play, which happens at 10. And that also has a -20 slope. So now we have -20, +20, those are canceling. So this extra -20 is going to force the overall slope to -20. So now the final slope of this magnitude plot is -20. And so this is the Bode plot of our transfer function. This is the magnitude plot. Now, this is only 1/2 of the Bode plot, because Bode plots come in pairs. This is just the magnitude. We also need the phase plot. And so the phase plot is going to be similar. So we're going to break it down, except now we're talking about that inverse tangent form when we were describing phi. So it's the imaginary over the real. It's that same format where we're breaking it down by numerator and denominator. So anything in the numerator will be added, anything in the denominator will be subtracted. Any constants are not going to have any value at all, no phase value, I should say. So we only have 3 terms here, 1, 2, and 3. So the first term will be tan inverse of omega over 2. It's really omega over 2 over 1 because it's the imaginary over the real, but because it's over 1, it'll just turn into omega over 2. Same thing with the next term. Omega over 10 over 1 is just omega over 10. The second term is being subtracted because it's in the denominator. And same with the third term. The third term is negative 90, and that comes from the table again. The table was telling us that if you have just j omega, either numerator j omega or denominator j omega, that it's either going to be plus 90 or minus 90. There's going to be no variation about it, unlike the other case where we're adding 1. So once again, we're just referencing our table, the phase column this time, instead of the magnitude. And in doing so, we're able to plot these 3 values corresponding to the table's interpretation. So it tells us that whatever that number is, 2 or 10, we're going to start a decade below that and then go for 2 decades past that. So 1 decade below 2 is 0.2. So we're going to go from 0.2 to 2 to 20, and it's going to cross 90 degrees. Similar here, it's going to go a decade below 10 is 1. It's going to go from 1 to 10 to 100, and it's going to cross negative 90 because we're subtracting it. And then that j omega term turned into negative 90, so that'll just be a constant value. That's this third value here. So we do the same thing that we did with the magnitude plot. We're just going to add our components together. So we're going to have, we're starting at negative 90 because that's the only thing that actually hits the y-axis. So negative 90, and then at 0.2 we would start our positive slope from this first component until we hit 1, where this is a negative component. These two have the same slope, so they're going to cancel out. So this will be straight until something changes. And the first change is going to occur at 20, where this component has ended. And because that's ended and this negative component is still active, this will be a negative slope once again until that ends at 100. And then it's a straight line. So this resulting solid line is the overall phase. And you combine that phase with the magnitude plot, and you have your Bode plot. And your Bode plot is showing you the frequency response of your system. And this came from the transfer function of your system, which you can derive by using circuit analysis of AC circuits and circuit analysis, which you're able to do by using phasors and impedances. And with all of this information, you can see how your system is going to respond at different frequencies and kind of hopefully answer that question of what is the frequency response and what output are you going to get for a certain input of omega. And that's all I've got to say about that. Thank you for listening.